You're listening to Arsenal for Democracy, episode 419, recorded on Monday, March 28th, 2022. I'm your host, Bill Humphrey. Joining me on the line from Idaho, as always, is Rachel. Hello, Rachel.
Hi, Bill.
This week's topic is synthetic dyes, another second industrial revolution product. Now, of course, humans have been changing the colors of things with dye since prehistoric times, but for thousands of years, these dyes were all based on things found in the natural world. By the early Industrial Revolution, some inventors were dabbling with experiments to see if they could come up with artificial colored dyes. But it was not until the mid-19th century that the synthetic dyes, based on chemistry and chemical reactions as opposed to physical reactions like, grinding something or burning it or whatever, were invented and mass-produced. This story, as we'll get into in a moment, starts in the United Kingdom, but as the first Industrial Revolution transitioned into the second, the story shifts overseas, as it so often did. Almost immediately, synthetic dyes became all the rage, launching a massive new industry and enhancing numerous existing industries, including, of course, fashion. On this week's episode, we'll discuss the emergence of synthetic dye and why it didn't happen until the period that it did, and we'll also talk about the environmental catastrophe of the synthetic dye industry, which is still ongoing, unfortunately. I'm going to go over the history as much as possible, and Rachel's going to explain some of the basics of things like the physics and the chemistry, and some of the more scientific uses of dyes, but basically, the physics and chemistry is important to understand because it makes certain subcategories of dyes behave in desired or undesirable ways, and it affects the coloration itself. But as I said, let's start with some general information or history about synthetic dyes. So for that, we start with Movine, which was the first mass-produced dye. Because as I said, in the 1700s, early industrial revolution, you do get some experimentation with dyes, but just kind of like when we talked about, inventing plastics and things like that, just because someone sort of invented a one-off thing by accident one time didn't necessarily mean that that's really when it became a thing. So for that, we need to go to the first thing that, gets your patents and your mass production, assembly lines, things like that. So for that, we got to turn to Movine, which was from 1856. So in 1856, and this would have been the end of the basically around the end of the first Industrial Revolution and just ahead of the second Industrial Revolution, British chemistry student William Henry Perkin was just 18 years old when he attempted unsuccessfully to use coal tar to synthesize anti-malarial quinine, which had been first synthesized a couple years earlier in Norway by a German chemist, basically using something else. But the challenge was, can you make quinine with coal tar? The answer apparently, at least in this case, was no. But what you can make instead, after purifying coal gas through the various stages of benzene and aniline, in Perkin's case, is inadvertently, he found a weird goop that faded to a pale purple. And he decided with a friend to figure out if this could be used to color anything. They quickly confirmed that it could be applied to textiles, specifically silk, and that it remained purple despite sunlight and washing. Perkin patented it and got his father and brothers to assemble capital investment to build a factory, and basically by 1857, the next year, had created a new synthetic dye industry from scratch, or at least they were working with existing natural dyers to get them to branch out. Eventually, synthetic dyes basically killed off the natural dye industry completely, with the exception of logwood, which is still chugging along in small but valuable volumes, much like it was in the 18th century golden age of piracy and illegal colonial harvesting on the Spanish Main, although now it is mostly used for modern medical usages that we'll discuss later. And this is what I've just talked about is mostly drawn from either the Britannica article on synthetic dyes or the Wikipedia article on William Henry Perkin, and also the one for quinine, and a little bit from I'm not even going to try to say the scientific name of logwood, but there's a Wikipedia page on logwood. In theory, Britain was well positioned after the first Industrial Revolution to take this innovation and run with it because of the many textile mills and the roaring coal-based heavy industry producing tons of coal tar byproduct that could be used to make dye. And for a few years, things were going well, and Perkin specifically did become a rich man and a very influential chemist, as did his son later. But ironically, in a further demonstration of why Britain started to fall behind in industrial development after the mid-19th century, despite the huge and revolutionary success of the chemistry research that was creating things like synthetic dye, the government and private industry got bored and disinterested with innovative research and scientific education after the 1861 death of Prince Consort Albert of Saxe-Coburg and Gotha, who had been pushing it at an official level in Britain for decades. And pioneering chemists like August Wilhelm von Hofmann, whose student, Perkin, had invented Movine, simply went home to Germany less than a decade later. German industry remained chemistry-oriented and still is. For example, one of the largest petrochemical companies in the world is BASF. This kind of trend helps explain why Second Industrial Revolution developments tend to originate in places like the United States or Germany, rather than Britain or France, and propelled them to rising second-tier power status with the infamously resulting consequences for the 20th century. But if we focus a little bit more on Movine just for a bit, there was a rapid takeoff in popularity of the new vibrant synthetic purple, which of course then in turn incentivizes working on other dyes. All of a sudden, for the first time in thousands of years of fashion history, Europe had a source of purple textile dye that didn't come from mollusk mucus and was no longer basically Roman emperor level expensive to obtain. Now, notably, the royals of Europe at the time were also quite interested in Movine. Queen Victoria and French Empress Eugénie both helped popularize the color. The new synthetic purple dye became a fashion sensation in Britain, France, and elsewhere under names like Movine or Mauve, and probably contributed a bit to the emergence of the off-the-rack mass-produced clothing industry that we've discussed in various past episodes. The actual molecular structure of Movine, interestingly, wasn't even understood until 1994, 138 years later, and there are more than a dozen variants of it known today. And this is something that I think Rachel's going to talk a little bit about, but basically a lot of this stuff was really trial and error. Despite the advances in chemistry at this point, a lot of these guys working on this stuff were just kind of messing around with, well, what if I change this or what if I change that? And they didn't completely understand how a lot of this stuff worked. Later on, you get very sophisticated chemical engineering. That's a field that emerges where you are specifically saying, okay, this has this property, this has this property. If I combine them in this specific way, this should be the result. But at this point, we're still talking about a very trial and error process. Before we get to the science, though, I want to bring in some statistics at this point from a fantastic and freely available quantitative study of the early 20th century synthetic dye industry, published in March 2021 in the journal Heritage Science by Eric Hagen and Jennifer Poulin. So this basically looks at a matured industry that has now been operating for at this point more than half a century. How have they progressed? What's the state of the synthetic dye industry in the world at this point, and especially in the United States? So from 1856 to 1924, some 1,200 distinct synthetic dyes were invented. The number of new colors being invented each year peaked around 1890, several decades after the start of the industry in 1856, although there were still sudden bursts of new dyes now and then as new chemical categories were explored. Now, the usage of specific types of dyes varied based on factors like production cost, how toxic it was, and fastness, which is the term that basically refers to how well or durably it sticks in the dyed product, usually though not exclusively textiles. Many of these early synthetic dyes simply did not hold up well to sunlight or washing. And, except in cases where the faded color look could be marketed as fashionable, or where a clothing company could specifically sell a garment as being a dazzling one-time event piece, the textile producers wanted something more durable. And in fact, there was often friction between the companies developing the dyes, the companies actually dyeing the textiles, and the companies trying to buy the finished textiles to sell to the mass public because of these challenges. Inventing new dyes and shipping them around the world during that period of globalization was also profitable to manufacturers because both activities, inventing new dyes and shipping them overseas, helped evade patents on specific colors. In 1916, even with World War I already underway in Europe, foreign dye importation to the United States was still a big business, and Commerce Department records showed almost 300 different colors being imported in volumes exceeding 10,000 pounds per year, with some of these individual colors being imported by the hundreds of thousands or even millions of pounds annually. Moreover, these colors were often broad classifications, with many subvariant tones from slight tweaks to the chemical processes and ingredients during production. But World War I was proving to be a huge crisis for American companies that had relied upon foreign dye imports from Europe, and especially Germany, which were now increasingly under supply chain pressure, and this is what spurred a U.S. government emphasis, including that Commerce Department report, on domestic synthetic dye production in the United States. So this is something that was interesting when I was researching this, as I kept thinking, well, this is odd. This is all about European dye production. Where's the discussion about the U.S.? Surely they must have been involved. But really, the U.S. domestic synthetic dye industry doesn't actually take off, despite this long period, until after this pressure from World War I, and then it really gets going. Compared to the nearly 300 dyes being imported in 1916, there were around 100 being produced in the U.S. in 1914 when the war began, and there were arguably around 900 different dyes in use by American industry if you count all the subvariants. So there was some forced substitution and consolidation down to a narrower number of dyes during the war. In 1914, in just the top 10 imported synthetic dyes to the United States, there were 3 different blues, 6 different blacks, and 1 yellow. Now, as we said, the industry gets kicked off with Movine, which is a pale purple, but, as I said, it rapidly takes off, and so you get some other things. So I wanted to just briefly mention a couple of those. So Perkins' accidental discovery, and this is now quoting from the Britannica article, Perkins' accidental discovery of mauve as a product of dichromate oxidation of impure aniline motivated chemists to examine oxidations of aniline with an array of reagents. Sometime between 1858 and 1859, French chemist François-Emmanuel Verguin found that reaction of aniline with stannic chloride gave a fuchsia or rose-colored dye, which he named fuchsine. It was the first of the triphenylmethane dyes and triggered the second phase of the synthetic dye industry. Other reagents were found to give better yields, leading to vigorous patent activity and several legal disputes. Inadvertent addition of excess aniline in a fuchsine preparation resulted in the discovery of aniline blue, a promising new dye, although it had poor water solubility. From the molecular formulas of these dyes, Hoffman showed that the aniline blue was fuchsine with 3 more phenyl groups, C6H5, but the chemical structures were still unknown. In a careful study, the British chemist Edward Chambers Nicholson showed that pure aniline produced no dye, which is interesting, and this was a fact that was also discovered the hard way at a Ciba plant in Basel, Switzerland, that was forced to close because the aniline imported from France no longer gave satisfactory yields. Basically, they needed impure imports, and the imports weren't impure enough. Hoffman showed that toluidine CH3, C6, H4, and H2 must be present to produce these dyes. All these dyes, including mauve, were prepared from aniline containing unknown amounts of toluidine. So fuchsine was basically a magenta dye when liquid, but a dark green when it was in crystal form, and it is today known as a confirmed carcinogen to workers producing it. But as we said, basically a lot of these things were variants of each other, and you just tweak them slightly if you can sort of figure out how to do that, even if you don't really know what you're doing. And you get various blues and vibrant synthetic greens and things like that. And eventually, with sulfur-based dyes, you get a lot of yellows and so on. So there's a lot of experimentation and increasing understanding of how to get the results that you want without just doing trial and error. But I want to turn now to Rachel at this point to talk a little bit more about the science with regard to the colors and sort of the state of the scientific field at this point in terms of understanding how any of this worked.
Right. So at the time, there wasn't a very sophisticated understanding of how humans perceived color and visible light. Um, at that point, there wasn't really much known about the visible spectrum, the electromagnetic spectrum. So it was just a lot of kind of conjecture, but based in fact, especially as advances in structural theory of chemicals led to investigations of correlations between chemical constitution and color. In 1868, German chemists Carl Graebe and Carl Lieberman recognized that dyes contain sequences of conjugated double bonds. So, for example, there's a certain element double bonded with carbon, which is just basically changed with more carbon that has double bonds, where the certain atom is a carbon, oxygen, or nitrogen atom at the end, connected to all these carbons in a chain. In 1876, German chemist Otto Witt proposed that dyes contain conjugated systems of benzene rings bearing simple unsaturated groups. For example, NO2, a double bonded nitrogen, nitrogen double bonded to another nitrogen, or carbon double bonded to an oxygen, which he called chromophores, and polar groups, so groups that have a charge to them. So, for example, NH2 or an OH group, which he named oxochromes. These ideas remain valid, although they have been broadened by better recognition of the role of specific structural features. Witt had also claimed that oxochromes impart dyeing properties to these compounds, but it later became clear that color and dyeing properties are not directly related. Witt suggested the term chromogen for specific chromophore oxochrome combinations. So the colors of dyes and pigments are due to the absorption of visible light by the compounds. The electromagnetic spectrum spans a wavelength range of 10 to the 12 meters, from long radio waves, which are about 10 kilometers, to short X-rays, which are about 1 nanometer. But human eyes detect radiation over only the small visible range of 400 to 700 nanometers. Organic compounds absorb electromagnetic energy, but only those with several conjugated double bonds appear colored by the absorption of visible light. Without substituents, chromophores do not absorb visible light, but the oxochromes shift the absorption of these chromogens into the visible region. In effect, the oxochromes extend the conjugated system. Absorption spectra, plots of absorption intensity versus wavelength, are used to characterize specific compounds. In visible spectra, the absorption patterns tend to be broad bands with maxima at longer wavelengths corresponding to more extended conjugation. The position and shape of the absorption band affect the appearance of the observed color. Many compounds absorb in the ultraviolet region, with some absorptions extending into the violet, which is the 400 to 430 nanometer region. Thus, these compounds appear yellowish to the eye, i.e., the perceived color is complementary to the absorbed color. Progressive absorption into the visible region gives orange at 430 to 480 nanometers, red at 480 to 550 nanometers, violet 550 to 600 nanometers, and blue 600 to 700 nanometers. Absorption at 400 to 450 and 580 to 700 nanometers gives green. Black objects absorb all visible light, white objects reflect all visible light. The brilliance of a color increases with decreasing bandwidth. Synthetic dyes tend to give brilliant colors. This undoubtedly led to their rapid rise in popularity because, by comparison, natural dyes give rather drab, diffuse colorations. So I'm hoping that wasn't too dense, but in essence, these synthetic dyes help reflect light into your eye and give you a brilliant color that just doesn't happen as much with natural dyes because they're a bit more drab and diffuse, because they're not bouncing at your eyes in those like longer wavelengths, basically. So hopefully that wasn't too broad or too dense of an explanation.
Yeah, thanks. So while the already gigantic textile industry of 1850s Great Britain and France were the natural first targets for applications of synthetic dye, there was a lot around the corner that was going to really make this industry take off, so that it wasn't just tied to textiles. The wood pulp paper industry was just about to emerge. Ink was going to be needed for all the new typewriters and newspaper machines, and there were plenty of opportunities to branch out in the use of these new synthetic dyes. Even dyed leather was a future use case. Paints and then PVC plastics, as we talked about on our episode on that topic, also use dyes, although that generally comes later. And we'll circle back in a bit to food coloring, which is often in the same category as other human consumable dye uses like cosmetics. But before we get to that, we've talked a little bit about the science related to the color, and Rachel mentioned that German chemist researcher Witt was speculating on the relationship, if there was any, between the color properties and the properties of the actual, what I referred to earlier as the fastness, basically how well does it dye the thing? Does it stick to it? Does it, not wash out? Does it not fade in the sun? That sort of thing. But it turned out that those were sort of two separate things. And that is sort of the flip side of the challenge, right? One of the reasons you get so many different colors or dyes being invented, as I quoted from that earlier study, is because you can invent a color, but then if it doesn't work for dyeing, it's not that useful. Or if it's too expensive and too much of a hassle, you got to find something else. So, Rachel, how does modern synthetic dyeing of materials actually work? How do they get it to stay in the thing they're trying to dye?
Right. So in dyeing operations, the dye must become closely and evenly associated with a specific material to give level or even coloring, with some measure of resistance to moisture, heat, and light, i.e. fastness, as we've been talking about. These factors involve both chemical and physical interactions between the dye and the fabric. The dyeing process must place dye molecules within the microstructure of the fiber. The dye molecules can be anchored securely through the formation of covalent bonds that result from chemical reactions between substituents on the molecules of the dye and the fiber. These are reactive dyes, a type introduced in 1956, so relatively late in the game. Many dye-fiber interactions, however, do not involve covalent bond formation. While some dyeing methods have several steps, many dyes can be successfully applied simply by immersing the fabric in an aqueous solution of the dye. These are called direct dyes. In other cases, auxiliary compounds and additional steps are required to obtain the desired fastness. In any event, questions arise as to how well the dye is retained within the fiber. The structure of the fibers from which the common fabrics are made provides some guidance for the selection of useful colorants. So to kind of go back to the bonding type we were talking about earlier, I'm going to go to some remedial chemistry. There are several types of bonds. So as I mentioned before, covalent, where molecules share electrons. There's also ionic bonds, where negatively charged and positively charged molecules are attracted to each other. Hydrogen bonding, which is an intermolecular force that forms a special type of dipole-dipole attraction when a hydrogen atom bonded to a strongly electronegative atom exists in the vicinity of another electronegative atom with a lone pair of electrons. And then finally, there's van der Waals forces, where molecules that are close together form a weak attraction to each other. And also, to dive into the chemistry is what these fibers are made of. So there's natural fibers, such as wool, silk, and leather, or cotton. So wool, silk, and leather are made up of chains of proteins, and cotton is made of chains of cellulose, which is a polysaccharide, a sugar basically. So these fibers are then spun into thread or yarn to be made into fabric. Now natural fibers are intrinsically porous, and these pores provide spaces for the dye molecules to bind to the fiber. Synthetic fibers, the most common being polyester, are made up of chains of synthetic analogs of proteins separated by hydrocarbon chains. The terminal hydroxyl group of these chains do provide a site for polar binding with dyes, but the chains themselves are packed tightly and are less porous than natural fibers. Acrylics are another synthetic fiber with more polar groups along the chain to improve dyeability, and there are also the semi-synthetic fibers such as viscose, which is made from wood pulp, and rayon. These fibers don't allow for hydrogen bonding, and different dyes are needed than for either natural or synthetic fibers. So there's a lot depending on what the fiber itself is made of, as to which dyes or dyeing techniques you're going to use. So as we mentioned before, there's direct dyeing, where the fabric is dyed in a hot aqueous solution of the dye. The dye is then trapped in the fiber structure with hydrogen bonding and van der Waals forces. Metal salts may be applied to the fabric beforehand to improve dyeability and fastness of the dye. These metal salts are known as mordants. Mordants also help vary the colors of dyes. For example, treatment with aluminum hydroxide, AlOH3, before dyeing with alizarin produces turkey red, the traditional red of British and French army uniforms. Alizarin gives violet colors with magnesium mordants, purple red with calcium mordants, blue with barium mordants, and black violet with ferrous salts. So there's a wide variety of treatments you can use to vary the colors of these dyes. So there's all these different combinations you can do to produce more colors. Another technique is disperse dyeing. This technique is used for polyester and other synthetics. The fabric is immersed in a boiling aqueous dispersion of insoluble dyes. So it's not a solution because the dyes are not dissolved in the liquid solution. The dyes then transfer to the fabric and react with the fabric to form a solid solution. The exact mechanism isn't known, but it's believed the chains relax from their tightly formed bonds to allow the dye in, then revert back to their tightly chained state. So DuPont has invented a technique that doesn't require a lot of contact time, not a lot of heat, so it helps retain the integrity of the fiber while allowing the dye to bond with the fabric. There's also vat dyeing. This is an ancient dyeing technique. So in this technique, a dye is converted from a soluble to insoluble state. So for example, indigo, which is a natural dye, comes from a plant. It's reduced to leuco-indigo, which is a soluble colorless form. Then cotton is immersed in the leuco-indigo bath. After the cotton is removed from the bath, the leuco-indigo is oxidized back into indigo. The indigo molecules form complexes that are too big to leave the fiber structure, and indigo is insoluble, so from that point on, the indigo is trapped in the fabric. This is most often done with cotton, like indigo blue jeans, basically, were made using this dye technique. Another technique is azo dyeing. This technique was developed in the late 19th century. A diazonium salt reacts with a coupling component to form a dye. So a fabric can be immersed in a solution of this coupling component, then a solution of diazonium salt to form the dye right on the fabric. Alternatively, the fabric can be treated with diazonium salt before immersion into the coupling component solution. So you could do the steps in either order. And so because the dye is formed right in the fiber, that chemical reaction is happening during the process of the fiber being exposed to these different reagents. Then the fabric has excellent fastness because the dye is basically ingrained into the fiber. And the last technique I'm going to talk about is reactive dyeing. So this technique directly links the dye to the fiber using covalent bonds. So this was a pretty rare, a pretty recent process. It doesn't happen very often. Most dyeing reactions happen by forming ionic or hydrogen bonding. But this technique was developed in the 1920s, but the bonding process of bonding the dye to the fiber led to degradation of the fiber itself. It wasn't until the 1950s that the process was perfected, and they were able to create these covalent bonds without actually degrading the fiber itself. This process is very effective for dyeing cotton and cotton poly blends. So it's a relatively new technique, and a lot of the shirts we wear today are cotton poly blends. So they had to create a dyeing method that worked with these blends of both synthetic and natural fibers.
Well, Rachel, I certainly appreciate you going into depth on this and going to the remedial chemistry stuff because I got a C+ in one term of high school chemistry. It was one of the worst grades I'd ever gotten because I'm not very good at the math stuff or understanding this. Also, as a side note, I completely forgot to mention this, but I was reminded when you mentioned about the treatment of putting together aluminum hydroxide with alizarin to get turkey red. Alizarin's another interesting one because that was historically a natural dye that was derived from plant roots, but in 1869 it was the first natural dye that was produced synthetically. Basically, they were able to recreate it through a synthetic process. So that's another important historical one, relatively early, although still more than a decade after Movine, to be produced as part of this emergent synthetic dye industry. Now, in 2021, present day, last year, the global synthetic dye industry was meeting a market demand for dye worth over $18 billion and still growing by nearly double-digit percentages in value annually. And apparently a pretty obscene amount of this market growth, according to trade industry reports that I read, is literally just packaging materials for other products, right? Dyeing the physical packaging, the cardboard or whatever, which is kind of horrifying to contemplate. And you think about all those, Amazon boxes and everything. That's all stuff that's getting dyed. And another rapidly growing submarket, which goes back to this, I think, probably the reactive dyeing and things like that Rachel was just talking about, is dyes suited to the specific stretchy component materials of sportswear and athleisure garments. So that was kind of an interesting, although worrying thing to read about. But let's talk about the one sort of other big, huge category of synthetic dyes that we see all around us in the modern economy and everyday life that everyone deals with at this point in the American supply chains, and that is food coloring. So, Rachel, could you tell us a little bit about some of the superficial or embedded coloring in foodstuffs?
Yeah, so a lot of this information came from the International Association of Color Manufacturers, kind of a trade group that is there to lobby and kind of inform the public on what they're doing exactly. So technically, color additives are any dye, pigment, or substance that can impart color when added or applied to a food, drug, cosmetic, or to the human body. And all those uses are kind of grouped together. Like we have the FDA, the Food and Drug Administration. So a lot of these regulatory bodies are kind of grouping the food, drug, cosmetic industries together. So a color additive is often considered to belong to one of two classes, natural color additives or synthetic color additives. This distinction is not always meaningful because there are some color additives that are considered natural that are produced through chemical synthesis. Whether a color additive is synthetic or natural has no bearing on its overall safety. Both types of color additives are subject to rigorous standards of safety prior to their approval for use in food. So there are three types of color additives. There's straight colors, which, as the name implies, they're not mixed or used in a chemical reaction with another substance, and they consist of dyes, which are soluble in water, or pigments, which are insoluble in water. There's lakes. So lakes are formed by chemically mixing straight colors with precipitants or substrata. Lakes must be made from certified batches of straight colors, with the exception of carmine, which is made from cochineal extract, or beetles, as you may have read about before. Lakes are used in applications where color bleeding is undesirable, such as like frostings. So if you're making a rainbow cake, you don't want the colors of the frostings to mix and bleed with one another and kind of make like a muddy brown or whatever. And then there's mixtures. So as the name implies, mixtures are formed by mixing one color additive with one or more other color additives, or one or more straight colors and one or more diluents. So they're really kind of trying to say that like food additives are safe, color consumable dyes are good, they're fine. So go ahead and eat your rainbow unicorn frosting and whatnot. You'll be fine. So what are the safety regulations for consumer dyes? Food coloring laws use a positive listing of permitted dyes rather than a negative listing of banned dyes. So in the U.S., the Pure Food and Drug Act of 1906 reduced the list of permitted synthetic colors from 700 to 7. As of 2016, there are still 7 dyes permitted in food, though not the same 7 as were permitted in 1906. There's also some special use dyes. There's a dye that's permitted to color orange peels, and there's also a dye used to color sausage casings that hasn't been produced since 1978, but it's never been officially delisted. So, in addition to these synthetic dyes, there's also several permitted natural food dyes, such as elderberry juice, annatto, turmeric, and caramel coloring. So, if you read your package ingredient lists, there's oftentimes you'll see that F, D, and C, so that's food, drug, and cosmetic, and then the color, so like red, and then a number. So we have F, D, and C, red, number 40, which I think is one of the more controversial food and drug dyes, but it is still permitted to this day. So that's kind of how you can parse it out. The F, D, and C means it's been approved by the FDA, and it's given a food, drug, and cosmetic number. In the EU, they're all synthetic dyes are preceded by an E and then a number, and the color is not included in the color name. So their packaging rules are a little bit different than ours. But still, they operate along the same principles of having a positive list of permitted dyes rather than a negative list of banned dyes or banned ingredients. Some other applications of dyes. There's research in medical dyes. So there's dyes used in studying samples. So for example, there's the H&E stain. This is hematoxylin and eosin stain used in pathology. So that hematoxylin we talked about previously is derived from that logwood, and it creates a blue dye that stains cell nuclei blue, and then eosin is a counterstain that stains extracellular material pink. So this HE stain is considered the gold standard in pathology. So it's used for looking at like cancer biopsies, just other like tissue samples. So if you ever get a biopsy, if you ever get a pap smear, that's the type of stain they're using to look for cancerous cells or precancerous cells. Another common stain is the Gram stain, which is used in bacteriology to differentiate bacteria based on the composition of their cell walls. So in this process, crystal violet is used to stain bacteria. Gram-positive bacteria have a thick layer of peptidoglycan in the cell wall that retains this crystal violet stain, while gram-negative bacteria have a thinner cell wall that doesn't retain the stain. Iodine is used to strengthen the cell wall crystal violet bond. Ethanol is then used to wash the slide, so gram-positive cells will still retain the violet stain and resist that washing with the ethanol, while gram-negative cells will have the stain washed away. A counterstain of safranin or fuchsin will then be applied to stain gram-negative cells pink, making it very easy to differentiate gram-positive and gram-negative cells. So kind of a note on the logwood used to create this hematoxylin or hematoxylin stain. There have been periodic shortages, and we may experience another shortage soon. Just supply chain issues used in acquiring the hematoxylin that is extracted from the logwood. So there's various points where the supply chain can get interrupted and create this shortage of the dye. There are substitutes, but they have to be similar enough to the H&E stain, or else they become hard to read. So pathologists are trained in reading these H&E stains, and if they're trained in a certain technique and then have to switch to a different technique that looks different and creates different colors on the slide, it can be difficult to accurately read the slides. So this can create issues in diagnostic testing as well.
And as we said earlier, logwood is unusual because it's one of the few remaining natural dyes that's still in use. So a substitute would probably end up being a synthetic substitute. But, you know, it's one of the few things that was a long-standing historic dye that's still in widespread use. But, you know, because it is a natural thing, you know, and you're harvesting it from the natural environment, that can lead to these sort of shortages. But we wanted to mention it just because dyes, you know, although we're focusing on synthetic dyes, there is this need for a new synthetic dye to replace this natural dye. That's an important part of medical and research uses.
Right. Another use is dye used in the human body for condition treatment. This is kind of a historical note, a historical usage in the 19th century. So in 1891, Paul Ehrlich discovered that certain cells or organisms took up certain dyes selectively. He then reasoned that a sufficiently large dose could be injected to kill pathogenic microorganisms if the dye did not affect other cells. Ehrlich went on to use a compound to target syphilis, the first time a chemical was used in order to selectively kill bacteria in the body. He also used methylene blue to target the plasmodium responsible for malaria.
Kind of bringing it back around to the early attempts to synthesize quinine, one of which accidentally created the synthetic dye industry in the first place.
Right, and as we've talked about before, antimicrobials or antibiotics are a very recent development. So being able to target syphilis or try to kill it off in this way, and was a way to kind of get around that lack of antibiotics at the time. So it's kind of an interesting use of dyes to selectively target these pathogens. There's also dyes used in the human body for diagnostics. So contrast dyes are used to improve imaging for CTs or X-rays. These are typically made from iodine when used like in the respiratory system or in the circulatory system, or barium sulfate if they're used to image the digestive system. So these contrast dyes can be injected or swallowed. MRI contrast agents, on the other hand, are used to change the magnetic properties of nearby hydrogen nuclei to change how they appear on the MRI, and as such aren't classified as dyes. So those are a few different ways we use dyes in different applications today.
So the last thing that we need to talk about is obviously the pollution consequences of this industry. There is a horrifying history of synthetic dye pollution over the past 166 years because the nature of applying most dye, which is why Rachel went into so much depth about how it's actually applied, it involves mixing it into water-based solutions and then often dunking an object or component ingredient into that solution until the dye takes, which still, at the end of the process, leaves a lot of colored wastewater. And when an industrial process finishes with wastewater, traditionally, this has simply been dumped right back into the local environment, such as a stream, river, pond, ocean, etc. And unless it's food coloring type dye, it's probably not good for local wildlife or the aquatic ecology, especially when it blocks sunlight in the water. A lot of these dyes are pretty harsh, toxic, or cancerous products derived from sulfur, acid, benzene, etc. Astonishingly, some developing economies still use one of the toxic or carcinogenic mid-19th century synthetic dyes, malachite green, as an antimicrobial solution in aquaculture, even though eating fish that have consumed malachite green has been a known serious risk to humans for decades. Shocking present-day volumes of dumping still continue, with the better case scenarios often still involving using carbon filtering on the wastewater to somewhat reduce the pollution content before its release, but then still leaving masses of toxic carbon filters to be dumped into landfills. In 2009, which was quite a while ago at this point, but still a relatively recent statistic, to give a sense of the scale of the dye wastewater problem, which has only really grown since then, China alone was generating 1.6 billion tons of dyed wastewater yearly. Chinese and American researchers at the time were working together on trying to invent various filtration and sort of sponge-like technologies or nanotechnologies that could clean up the wastewater. We'll see how that goes. That was from a chemistryworld.com article back in 2009. Some of the articles that I read, like there was a book review I found on ScienceDirect.com, but who knows? I didn't read the book. Suggest that there's some possible hope for, some kind of eco-friendly but still artificial dyes. This would be part of the so-called green chemistry field, but that sector has yet to really prove itself, right? And it's unlikely that everything is going to be converted to harmless food coloring because, as we talked about, one of the big challenges for the dye industry, whether it was the natural one historically or the synthetic one after the 1850s, is that you have to get the stuff to stick and not dissolve in when it goes into the washing machine, or if it gets rained on, if it's an outdoor product or whatever. You don't want your house siding to fade in the sunlight, etc. So there's all these factors that make them want to get the most durable and least degradable type of dye, and that is inherently in conflict with biodegradation, essentially. Maybe you could come up with something that's like, oh, it'll degrade after 50 years or 70 years or whatever, but, we'll have to see how that goes. Some emerging market countries like India have actually banned certain kinds of synthetic dyes completely in favor of all natural dyes because the synthetic substitutes are simply too ruinous to the environment and public health to tolerate importation or local production. And that's according to an article from thebusinessresearchcompany.com. As always, all the articles and citations that we've made today will be up in the notes in a PDF at arsenalfordemocracy.com. But Rachel, I don't know if you had any sort of closing thoughts on whether it's the pollution issue or the wider topic of synthetic dyes, which I didn't really know a whole lot about before we started working on this. And it's kind of an unusual one for us because it's relatively limited in its U.S. relationship, except that the United States used a lot of it from elsewhere for their own other industries.
Yeah, touching on the pollution aspect of things, I think a lot of companies are trying to explore going back to natural dyeing techniques. But then you have the problem, like I mentioned, they're just not as brilliant or bright as synthetic dyes. So I don't know if there's like a re-education or a shifting of aesthetic preferences that we kind of need to go through. But we might have to switch to some of those natural dyes and get rid of the synthetics, and then maybe, I guess, just get used to kind of the more granola-y looking, like blues and greens that are kind of, I guess, like kind of faded or kind of drab looking, but
I guess that's part of degrowth, right? Is getting
yeah.
into the mindset of, well, we don't need that many colors.
Yeah, exactly. And another interesting development is breeding cotton to create colors. So there are different colors of cotton. It's not just the white that we think about when we visualize cotton. You can grow cotton in like browns and like greens. And they have spun fiber out of that cotton, and it doesn't need dyed, or you can dye over it. But it is kind of a more crunchy look. It does look very natural. So I guess maybe we just have to get people turned on to that sort of aesthetic rather than these garish, bright, brilliant colors.
All right. Well, Rachel, thank you so much for being on this week to talk about the history of the synthetic dye industry.
Thanks. It was a fascinating topic.